knowledge, yeah, just basic knowledge. Yeah. So you do not need to worry too much. Yeah. First, I want to review the basic knowledge a little bit. Okay. All right. Yeah. Yeah. Standard form of linear systems of ODEs. Yeah. All right. Yeah. So here, we are familiar with the algebraic linear systems. So now we need to consider differential linear systems. Yeah. All right. That's the algebraic linear system. Yeah. So we do comparisons. Yeah. All right. And usually we like to use the matrix form. Yeah. Capital A, the coefficient matrix. Yeah. And so here, yeah, because on my PowerPoint slides, I can use boldface. Yeah. So when you write on your papers, it's not that easy. Yeah, but we understand the meaning. Yeah. So when you write the symbols, yeah. All right. Yeah. So this is the algebraic notations. Yeah. But when we move to move to the differential linear system. Yeah. We have the similar. We use the similar way. Mainly the matrix form. Yeah. Because that's compact form. Yeah. So we like to use the matrix form. So we do not need to, write down the long equations. Yeah. All right. Here our matrix form of ODE. Yeah. Y prime equals capital A times Y vector and a plus G vector. So there is a G, the function part, vector of functions. So Y prime, yeah, we know the meaning, a straightforward meaning. So Y vector and the G vector. Yeah. All right. So now we need to study the basic properties. Yeah. All right. Yeah. So first, let's look at simple example. Yeah. Yeah. So we're familiar with free motions of mass spring damped system. Yeah. It's not in linear system form. Yeah. But we convert it to linear system form. Yeah. All right. Yeah, so that's the problem we studied before. Homogeneous second order ODE. Yeah. So this simple second order ODE. Now we want to convert it to linear system. Yeah. All right. So the conversion, remember, it's the last time in Module 3. One part of Module 3, we did that conversion. Yeah. We wrote the formula of conversion. Yeah. Here we apply the similar idea. Yeah. At that time, yeah, when we represent higher order ODE, we can use a first order linear system to represent nth order ODE. Yeah. So we use that method to do the conversion. Yeah. Here, yeah. So before we do the conversion, let's write in this standard way. Yeah. Then we need to introduce some new functions in order to bring down. Yeah. Here we need to bring down the order of derivatives, second order derivative. Make it first order. Yeah. So we need a y1 function corresponds to y2 function. Yeah. Yeah. So y prime, we use a new function, y2, yeah, for y prime. In this way, y double prime, that's y2 prime. So first order. Yeah. So with one more function, yeah, so that's the cost. That's the when we do this conversion, we need to pay. No. So that's the cost, extra cost we pay here. All right. Yeah. So the gain, after we pay, so we have gain. The gain is we only have first order derivative. We will not have second order. Yeah. In this new system of ODEs, we won't have any second order derivative expressions. Yeah. So now we get a simple linear system. Yeah. What do you see? You only have y1 prime, y2 prime. Yeah. But you have two equations. Yeah. Two equations. Yeah. Instead of that one equation. All right. They are essentially the same, right? Yeah. Equivalent. We can say these two forms of ODEs completely equivalent. Yeah. All right. So then you may ask the question, why we want to do this kind of transformation? We change the form. What's the benefit? Changing to a new form. Yeah. It looks like not necessary, right? Yeah. Because we know how to solve this ODE easily. Yeah. Very easy. Yeah. Yeah. So why you use this new form? It looks like more complicated than the old one, right? Yeah. So, yeah. All right. So here, I think the reason we do this is, we know when we use a completely different form, we change our view of understanding. Right? Yeah. When we work on different ODEs, basically we want to understand the problems. Yeah. All right. So you have two different ways to understand problem. One is this way. Okay. Another is this way. Yeah. These two ways quite different. All right. Quite different in the form. Outside forms different. Inside content, no difference, right? Inside content, completely the same. But the outside forms quite different. Yeah. Do you have your own real life experience, like for things like this? Yeah. Same content, but they are displayed in different forms. The same content, in different forms. Yeah. Something related to, as I remember, yeah, something related to philosophy. Philosophy, content, right? The forms, content, yeah, relationship. Yeah. All right. We know the content is the most important thing, right? Yeah. Fundamental. The content is the fundamental part. Yeah. Yeah. Outside forms, that's the presentations, right? Yeah. So you present your content in this way, a different way, many different ways, but content is the same. Okay? Yeah. But here, another aspect also important. When you present the same content in different forms, actually, it changes your view of this problem. You use a completely different view to understand the problem. That's important. Yeah. When you have a different view, then you may have different solutions. Different solutions. No. Because different views can expose different properties. If you use this first view, some property is hidden. You cannot find those properties. Very hard to find some deep hidden properties. Now you change its presentation form in this way. So you have a different angle to view the problem. Suddenly, those hidden properties are exposed, revealed. So you can find those properties. That's the importance. So why people change the views. In problem solving, changing views very important. Changing views, you can have new ideas. You can find new properties, new ideas, and you can apply new methods to solve same old problem. That approach is important. Here, we take that approach. Now, with this form, we move to a different area of math, linear algebra. In the old form, we can not apply any result from linear algebra, right? We cannot. We can only apply the knowledge from polynomials. Knowledge from polynomial we can apply. But we don't know how to apply linear algebra, right? Because, the order is higher. Linear algebra, we only work on first order mathematical objects. Here, the second order mathematical objects. So it does not fit the framework of linear algebra. After we change the form, this time we only have first order mathematical objects, right? So now it fits the framework of linear algebra. So suddenly, we can apply so many well-developed linear algebra results on this equation. So you can see how important it is. There are many well-developed results in linear algebra, very powerful tools, right? In linear algebra. Now we can apply on this systems of ODE. So that's the reason. All right. So let's continue. We want to see the remaining part of this this example. All right. We still here we use the compact form. So here you can see there are two different forms. So, some very abstract. Okay, abstract, short, compact form. More explicit. So more detailed informations. So which way we should use? So we choose these two different ways. When necessary. If we do not need to use a lot of details, then we prefer this compact form. If we need to use the detailed information, then we get to that form. All right. So the symbol, the meaning of the symbol, capital A corresponding to, this equation. All right. So the four coefficients, 2 by 2 matrix. All right. Then G. So this equation there, because homogeneous, this right-hand side, that's the G function part, right-hand side. All right. So this G vector of function, it's a zero vector. All right. So we have a homogeneous linear system of ODE. Very simple. All right. So in linear systems, we also have that homogeneous concept. All right. Now, then in linear algebra, we also have this concept, characteristic equation. So what is the characteristic equation? corresponding this A matrix. All right. Yeah. So the characteristic equation for this second order ODE, we know. Yeah. So that's the characteristic equation. Yeah. Right? Yeah. So, all right. Yeah. Then we want to get the the version, the version in this linear system. Yeah. All right. Let's recall, how do we get this version of characteristic equation from this homogeneous second order ODE? We use the solution structure, this structure, E function structure. Yeah. 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 All right. Yeah. Y1, Y2. Yeah. Y. Yeah. Right. So, I mean, because derivatives are here. Remember, when we do the conversion, our Y2 is Y prime, right? Yeah. Y2 is Y prime. Yeah. And this is Y in our conversion. So Y2 should be the derivative of this function. Yeah. So by the chain rule, so Y2 should take this expression. Yeah. Related to the special case for the characteristic equation. Yeah, so we have this version. All right. Then let's write y vector. This is y vector. Okay, all right. All right. Then y prime vector. Yeah. Another round derivatives. Yeah. Derivative of the first component, derivative of the second component. Yeah. So y prime vector. Yeah. All right. Then let's get to, yeah, all right. Yeah, so before we get into the original equation, we observe y prime equals lambda minus lambda. Lambda is a scalar number, right? It's not a vector. So vector, scalar. So y prime, yeah, because from here, y prime vector, you can factor that y, lambda out. You can factor lambda out of this y prime vector. So you can easily see after you factor that lambda out, y prime vector equals lambda times y vector. Okay, very easy. All right, so we can see that. Then we need to combine with original equation. Both equations are true. Original equation and for our special y vector, we have two equations. Okay. All right. So we can replace y prime in the original equation by this lambda y vector, right? Yeah. We eliminate derivative. Yeah. All right. So now we need to review basic properties of linear algebra. Yeah. Now, so here, we want to see what condition this lambda should satisfy. With these two equalities, for what kind of lambda it can satisfy both equations? So that's our question. So we need to use basic properties of linear algebra to see the new equations for lambda. All right. Yeah. So scalar multiplication of a vector. Yeah. Yeah. So scalar a times a vector equals that. Yeah. So yeah. All right. So now we get here. All right. Replace y prime vector by lambda times y vector. Now, in this new equation, y prime is gone. Okay. That means we do not have ODE. Yeah. In this new equation, we only have algebraic linear system. Yeah. So it's not a differential linear system. Yeah. And we're familiar how to work on algebraic linear system. Yeah. So here we apply the basic knowledge of linear algebra to solve this algebraic linear system. Yeah, very easy. Yeah. Let's solve it. Y vector in the first term, y vector in the second term, common. Y vector is common in these two terms. Yeah. So we can factor it out. Factor y vector out. All right. Yeah. All right. So to do that, yeah, so here, we need to do it in a right way. Yeah. Because in the matrix vector multiplication, the rules we use in matrix vector multiplications slightly different. Yeah. Some of the properties are quite different from our scalar multiplications. So we're familiar with number multiplications, right? Not a vector-based multiplication. We're familiar with number-based multiplications. Yeah. So when we work on the vector matrix-based multiplications, we should be very careful. Sometimes it could be wrong. If you use the number-based multiplications to do the calculation, sometimes you could be wrong. Yeah. So we should be very careful. All right. Let's look at 2 by 2 identity matrix. Sometimes we need to use this special matrix. So we use notation I sub 2, the size 2 by 2. Yeah. Identity on the diagonal entries, 1. All the other entries, 0. That's identity matrix. Yeah. Very basic, but very important. All right. Yeah. Multiplication of the identity matrix and the vector. Yeah. So when we use identity matrix, multiply any vector, it does not change the value of that vector. Yeah. Because that's the reason we call it identity matrix. Okay? No change. What's the identity of our regular number-based multiplication? There is identity concept. Yeah. So here, at this point, we talk about this identity. There is an identity concept. Yeah. So let me. Yeah. In math, this identity concept, very basic, yeah, but useful. All right. In our number-based multiplication, there is this identity concept. What's that? Number-based multiplication. There is identity object, 1, right? Because 1 times a number A equals A. Yeah. So here, identity. So if you apply certain operation, here multiplication is the operation. Okay. So this, when we here we are talking about multiplication. Identity element and a general element, the result is that same general element. Identity element does not change the general element when you apply certain operation on it. Yeah, so here, in number 1 is the identity object. All right, if you use the same understanding, yeah, because people want to go abstract way in math, yeah, yeah. So when we work on some concrete objects, yeah, so our view very limited. Sometimes we need to raise our views to a higher level, abstract, so we can, understand in a different level. Yeah. Here, how about we change multiplication to addition? Yeah. Certain operation, the operation could be addition, right? Yeah. The operation could be addition, not necessarily multiplication. So when we change to addition operation, what is the identity object with respect to addition? element. Okay? Is it that 0? 0 plus A equals A, right? Yeah. So that means 0 is the identity object with respect to addition operation. See? Yeah. So here, I want to, describe this identity object in math. Yeah. All right? Then, in the high dimensional, so this we work on one dimensional environment. Yeah. Now let's work on two-dimensional environment. Okay? This time our identity object, the 2x2 matrix, special 2x2 matrix, this is our identity object. Okay? All right. Yeah. Then 3x3 n by n. So you understand the identity object. Okay. All right. Now, we should use the identity object here. Okay? Yeah? So when we need to factor this common vector factor out. Yeah, why? We want to factor y vector out. Then, after you factor y out, this lambda, the second term, you need to use the identity matrix. Okay? You need to use the identity matrix. Otherwise, you get something wrong. You get an expression not compatible. Not compatible. Yeah. So let me show you the factorization step. All right. Multiplication, 2x2. 2x2 matrix and a vector. All right. Yeah. Yeah. This is the definition of multiplication. So you have a 2x2 matrix, then you need to multiply it to this vector. Okay? Yeah. Two-dimensional vector. Yeah. So that's the the way you do the multiplication. All right. So now here, can you see? Yeah, because, so here, can you see lambda times y equals lambda times identity matrix times y. Can you see that? Okay, yeah. Because y vector equals identity I2 times y, right? Yeah. Y equals, so this is y, So y itself equals I2 times y, right? Identity does not change the value of the object, right? Yeah. So here we want to replace lambda times y expression by lambda times I2 times y. Do that substitution before we do the factorization. Yeah, our goal, we want to factorize y out. Yeah. But before you factor y out, this is a more friendly version than this one. More friendly version. Okay? All right. Yeah. So why more friendly? Yeah. All right. Now we can do the factorization. Factor y out. Inside A minus lambda times I2. Okay? Yeah. Because if some students, if you are not familiar with linear algebra, when they do factorization directly, if you ignore this I2, that is wrong. Okay? Yeah. If you just work on the form, because if you use the experience in our algebra factorization, if you miss this I2 matrix, you get something not compatible. Because A matrix minus lambda number, how can you use matrix minus one number? Right? Different objects. You cannot do subtraction. So you have to use one matrix minus another matrix. And these two matrices must have the same size. Then you can do subtraction. Same size. Between same type of So subtraction operation can only be defined between two same type of objects. Yeah. Yeah. Same type. 2 by 2 matrix A, 2 by 2 matrix lambda times I2. Then you can do subtraction. Okay? All right. Yeah. All right. Now we have this new linear system. Yeah. All right. Certain 2 by 2 matrix inside parenthesis. We have a 2 by 2 matrix. Okay? Certain matrix times a y vector equals 0. All right. What can we get here? So in our linear algebra, in this case, what conclusion can we get? All right? Yeah. 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 Let's go back to algebra. Algebra, if we have two numbers, number A times number B equals 0, what can you get? The product of two numbers equals 0. One of the two operands must be 0, right? Yeah. All right. Now, we are in the two-dimensional world. Okay? Yeah. So there, 2 by 2 matrix times a two-dimensional vector equals 0. What conclusion can you get? Yeah. Yeah. You should not use the analogy from our algebraic experience. Yeah. So one of the two objects must be 0. That would be wrong. Okay? You cannot say that. Yeah. Because in our two-dimensional space, yeah, here, yeah, because mathematically we do not call it world, we call it space. Okay? 2D space, 3D space, 1D space. Here, we are working in the 2D space. In this 2D space, these two, the product of these two objects equals 0. We cannot say one of the objects must be 0. We cannot say that. So it is possible both objects non-zero, but their product equals 0. Space. Yeah, completely different from our 1D space. Yeah. In 2D space, the two 0 objects equals 0, but both operands, non-zero. The matrix non-zero, the y vector also non-zero. That could happen. Okay, that could happen. Yeah. All right. So now we need to know the condition. Under what condition we get this equation? Yeah. All right. The condition is the determinant of this 2 by 2 coefficient matrix equals 0. If determinant equals 0, yeah, then we have this conclusion. Yeah. So here is. Yeah. All right. Yeah. So yeah, let's say in this way. If we have this equation, then we can conclude. This equation, and another thing is, y vector is not 0. Okay? Yeah? Yeah. We have this, and the y vector not 0. If y vector is 0, then any 2 by 2 matrix times 0 vector equals 0, right? Yeah. So here, we call y0 in this equation we call the y0 is a trivial solution. Yeah. 0 vector times any 2 by 2 matrix equals 0. So that 0 vector, it's a solution. Yeah. So we agree. 0 vector is a solution of this homogeneous. This is a homogeneous equation. But we call it a trivial solution. Okay? Trivial solution. We are not interested in the trivial solution. Yeah. Yeah. We are only interested in the non-trivial solution. That's meaningful. Trivial solution, not useful. So here we are only interested in the non-trivial solution. Now, how to get non-trivial solution? We assume y vector not equal to 0. Now, under this condition, we get a non-trivial solution. All right. Then, the simple result is like this. Under what condition this homogeneous linear system has a non-trivial solution? That's the question. Okay? Yeah. So we have a homogeneous linear system. We know it must have a trivial solution. But we want to consider non-trivial solution. Under what condition a homogeneous linear system has non-trivial solution? That condition is the determinant of the square coefficient. Yeah, it's a 2 by 2 square matrix. Determinant of the square coefficient matrix must be 0. Yeah? Yeah. For non-square matrix, we cannot define determinant, right? Yeah. Determinant can only be defined on the square matrices. Yeah. Yeah. Cannot be non-square rectangular matrix. Yeah. Because our linear system is sometimes we may have the rectangular non-square coefficient matrices. Now it's possible. Yeah. Yeah, but here when you use identity matrix must be square matrix, right? Yeah. So when you use identity matrix, must be square matrix. So there is a definition of the determinant. Yeah. Determinant must be 0. Yeah. Then we can find a non-trivial solution of this homogeneous system. Yeah. All right. Next, let's look at the determinant. So now we have this condition we can use. All right. Let's calculate that determinant. Yeah, here. All right. Determinant equals 0. All right. All right. A homogeneous linear system with non-trivial solution. Yeah. Here I put the result we just used here. Yeah. Yeah. Square matrix A. Here, this A matrix must be a square matrix. A times x vector equals 0. Yeah. If and only if. Yeah. So here, this A. Yeah. So when we write this, we must emphasize we only consider the non-trivial solution. Yeah, non-trivial solution. Okay. Yeah, non-trivial solution for x. Yeah. All right. If and only if the determinant equals 0. Yeah. And here, the size of A could be any size, n by n. Okay? Yeah. Yeah. It's not necessary 2 by 2. Yeah. So this result, a general result, n by n. Also works. Yeah. Yeah. Any dimension n. Yeah. Yeah, we have this result. All right. Yeah. All right. So now, yeah, our y vector we know non-trivial, right? Yeah. So if we go back to our, the damped, mass spring system, yeah, yeah. So our y is in this form. determinant not equal to 0. Yeah. So here, another simple, another algebraic, linear algebra property. Yeah. We also need to related to our result here is if the determinant is not equal to 0. Yeah. So here determinant equals 0 case. Yeah. We also the determinant of A is non-zero, then this A matrix is invertible. Invertible. This concept. Matrix invertible. Okay? Matrix invertible. That means the inverse of this matrix exists. Inverse. There is inverse matrix. In other words, if the determinant of A equals 0, like this one, A is not invertible. Okay? There is no inverse matrix for this matrix. If its determinant equals 0, not invertible. Yeah. All right. So that concept. All right. Yeah. So if A is invertible, then its inverse exists. Yeah. So think about if A is invertible, can we multiply its inverse both sides? Yeah. There is an inverse matrix of A. Yeah. If we multiply the inverse matrix, yeah, the left-hand side there is an inverse matrix, A inverse. Then right-hand side will also multiply A inverse. A inverse times 0 equals 0. A inverse times A equals identity matrix, right? Identity matrix times X equals X. So we can get X equals 0. This tells us if A is invertible, then the homogeneous system, A times X equals 0. This is a homogeneous system, only has a trivial solution. That homogeneous system does not have non-trivial solution. Only trivial solution if A is invertible. Okay? Yeah. So here we review linear algebra, the simple results. Yeah? Because many students may forget these basic results in linear algebra. But we need to use in our discussion. So that's why today I go very slow, yeah, because later we need to use this kind of basic knowledge frequently. Yeah. So I just go through once. Yeah. All right. Now, only trivial solution. All right. Now, regarding the matrix inverse object, okay? Matrix inverse object. We have the basic properties. A times A inverse equals A inverse times A equals I. That's the basic property. Okay? All right. Yeah. Yeah. Very basic. Yeah. The product of these two matrices, A and A inverse. Then we change the order of the product. Here, some of you may feel strange. Why, when we change the order, we need to write it another time? Yeah, because in our one-dimensional algebra, 1D, yeah, so we talk about multiplication between two numbers. Yeah. A times B always equals to B times A, right? Yeah. So we know, we call it commutative property. Yeah. Multiplication is commutative. Okay. Addition also commutative, right? Yeah. Multiplication also commutative. Yeah. But in matrix multiplication, we don't have that. We don't have that commutative property for multiplication. For addition, we have. Addition, A plus B equals B plus A. We have it. But in general, in matrix multiplication, A times B in general is different from B times A. So not the matrix product is not commutative. So here I emphasize that. Yeah. Because in general it's not commutative. So here these two matrices commutative. So that's why we write it explicitly. Yeah. Yeah. Okay? So they both equal this identity matrix. Yeah. All right. Yeah. Now we can work on this this we call a characteristic equation. Matrix version of the characteristic equation. Okay? All right. Determinant equal, yeah. Oh, not this one. This is the characteristic, not that one. Okay? That's the homogeneous linear system. This is the matrix version of the characteristic equation. This one. Okay? All right. Now we need to calculate characteristic. A time minus lambda I2, yeah. So, on the diagonal entries, A, yeah, remember A is 0. 0 minus lambda, yeah. And this entry, negative C over M minus lambda. Other entries, no change. Yeah. All right. Then let's calculate determinant. We have the determinant formula. Yeah. So determinant formula. The product of diagonal entries. Okay. All right. Then multiply the product of these two entries. Yeah. So after simplification, you can see that this equation is the same as the characteristic equation of the original second order ODE. Right? Yeah. So we use a completely different understanding. Yeah. So this determinant way, yeah, that's a different understanding. But at the end, we get the same result. Yeah. That means compatible, right? Yeah. So we have two completely different views. Yeah. Yeah. But when we work on the same object, yeah, so at the end, we get the same thing. That means compatible. Yeah. So these two views are compatible. Yeah. All right. Yeah. So we use this simple example. So you can see we go over all these basic linear algebra concepts. Yeah. All right. Yeah. Linearity principle, basis, Wronskian. Yeah. So we have the similar concepts in our linear system case. Yeah. All right. Superposition linearity principle. Yeah. Yeah. This time we use the linear, we'll use the vector version. Yeah. Vector version of the solutions. Yeah. So y1 vector, y2 vector, solutions of homogeneous linear system. Yeah. Yeah. ODE on some interval. Yeah. So is any linear combination. Yeah. So linear combination of two vectors is also a solution of that same system. That's the linearity property. Yeah. Linearity principle. Yeah. 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 It's very easy to see it. Yeah. All right. Yeah. So then the basis. Yeah. We also we need to use the basis concept. Yeah. All right. A set of n linearly independent solutions. Yeah. Linearly independent solutions. Yeah. Yeah. That's the meaning of the basis. Yeah. If we have this set of solutions, then we can represent the general solution as a linear combination of these basis vectors. Yeah. So, these functions are vector functions, vector valued functions. Yeah. All these n functions are vector valued functions. So now our general solution vector of functions. So it's a linear combination of these n solution vectors. Yeah. So that's simple. Okay? Yeah. All right. Now, arbitrary constant. Arbitrary constant, here you can see they are scalar constant. Yeah. Scalar constant. Okay? Yeah. Yeah. C1, C2. Yeah. Scalar constant. All right. Yeah. Fundamental matrix. Now, another concept called a fundamental matrix. Yeah. Because these vectors, these n solution vectors, they are the fundamental elements to build general solution. The general solution, we use these basic elements to build. Okay? So we put these n basic elements together so we get a fundamental matrix. Capital Y, that's our fundamental, we define. So it's a square matrix, n by n, square matrix. How to get a capital Y? We put these n vector value solution functions, we pack them in one matrix. We use this solution as column vectors. Okay? Yeah. Each solution, y1 vector is the first column of this capital Y matrix. y2 vector is the second column of capital Y matrix, and so on. Okay? So column vectors. We pack these n column vectors in one matrix, so we call this matrix fundamental matrix for this linear ODE, linear system of ODEs. Yeah. Yeah. All right? Yeah? Just some basic concept. Then, the general solution, yeah, after we have this concept, fundamental matrix concept, the general solution Y can be represented as capital Y times C vector. Yeah. So here, yeah, boldface C means a vector, right? So these C1, C2, these coefficients, not boldface, okay? So they are scalars, all right? So here, the C vector, yeah, so is a column vector. So here, the T, yeah, because here I want to save space, I use the row vector, but I do transpose. The T at the corner means transpose of this vector. So we make it column, okay? When we do transpose operation, we change the row vector to column vector. Yeah. So this C is a column vector. Yeah. So the product of square, capital Y matrix, product, Y to this column C vector. Yeah. So that's the representation of our general solution. Yeah. Yeah. Can you, do you feel comfortable? Yeah, so here, yeah, because I pause a little bit here is, you need to feel comfortable. Yeah. So can you see expression here? We can write as capital Y times C. Not C times Y, okay? All right. Not a C. Yeah. You cannot change the order. Yeah. You cannot change the order. Okay? Yeah. So Y, capital Y times C. Yeah. So you need to feel comfortable. Yeah. So yeah. Because what you see here, the product here, yeah, we know Y, Y matrix, each Y vector is a column vector. Okay, all right. So let me write it in this way. Yeah. Although some of the students have no problem on this step. Yeah. I'm afraid some of you may still have problem to see it. Okay? Yeah. Because we do not have much time left, only 2 or 3 minutes. Let me only explain this small question. So then we finish this slide and also today's class. Yeah. For those students who couldn't see how to get it. All right? Yeah. All right. So here, the form of this one, yeah, we just rewrite this form. But when we rewrite, we need to arrange the elements carefully. Okay, all right. So y1, y2, yeah, column vectors, yn, yeah, okay, yeah. So in this form, all right. Then the product C1, C2, yeah, dot, dot, dot. So I do not need to write Cn, okay? Yeah. In column vector, okay? The C vector in column vector. When we do multiplication between them, yeah, how to do multiplication? The multiplication of that equals this. Can you see that? Yeah. When we do, matrix multiplication with a vector, matrix vector multiplication, we do multiplication in this way. Okay? That's the definition of matrix multiplication. Yeah. So this follows from the definition of matrix vector multiplication, right? But this one, this part, capital Y, okay? Yeah. This part, C vector. Yeah, C vector, okay? All right. So that's the reason you have this. But you cannot change the order, all right? If you change the order, it's wrong. Yeah, you cannot change the order. The order is important. The order matters. When you work on matrix vector multiplication, yeah, you need to be very careful on the order of operations. Yeah. Yeah. All right. Yeah, let me stop right here. Yeah. So we will finish remaining part next time.